Okay, good morning, guys. This is an interesting video here about the Haber process. One thing that's observed about nitrogen, nitrogen is pretty unreactive especially compared to oxygen. And so let's take a look. And so Haber developed a process for reacting nitrogen in air. Um, there are things that do react with nitrogen in air. Those are nitrogen fixing bacteria. But chemical processes, it's not so easy. Those bacteria have certain enzymes that allow it to react. And so one of the things we want to do with the theory, at least try to understand these types of observations, the reactivity of nitrogen versus the reactivity of oxygen. And so here's the reaction of nitrogen with hydrogen. That's it. Let's take a look at this video.
Alive needs nitrogen in order to build the most basic bits of life, like amino acids and DNA. But for most of life's history, converting nitrogen to biologically
Maybe I had it. I thought I was muting the microphone, but I muted everything. So it was just, they were just talking about nitrogen. A lot of nitrogen containing compounds are used industrially. Ammonia is one of them. Ammonia, ammonium, nitrates, nitrites, those types of things. And so this is why it's an important process. These are 6 chemical reactions that changed history, but there are many more, obviously. And the calcium oxide with the concrete wasn't even listed here, so I put that as one of them. Silicon was listed. What else was listed here? Yeah, this is, of course, this is debatable. All right, let's take a look at chapter 11 here. And so today, my plan is to go through chapter 11, and then we'll do the lab. There'll be a break, kind of an extended break between chapter 11 and the lab. So these PowerPoints I didn't have up. Also, were there any questions before we get started here? No. All right. Well, let me do one other thing before I do this. I need to take a look at, I posted the key for the exam. I got delayed, sorry. I'm gonna return this to you tomorrow. I'll just email it back to you. The graded test. Some of these I accepted different. different answers. Like this one was actually my typo. I wanted 2.54, not 2.45. So it wasn't supposed to be a trick question like that. That was it. And this, you know, this was corrected on Piazza. This was supposed to be not square, but cubed here. Oh, what else did I do? There was one other one. Oh, yeah. The other one was this, you know, chemists are I should have said are most concerned, but I didn't have enough room here, but chemists are most concerned with electrical forces. But if you put down all, then yeah, that's true too. They are concerned with these as well, you know. Okay, I'll get to that in a minute, Crystal. This one threw people off. The gas is this kind of beige thing inside the container here. You know, this is open to the air. And so the gas pressure is much lower than the air pressure out here. The seesaw, you can see the seesaw misbalance. This one, you know, a lot of people miss this one because this is PSIG, gauge pressure. So what we have to do is we have to convert that into PSIA, absolute pressure, before using it. You know, absolute pressures and absolute temperatures are what we use for the gas laws. Otherwise, we have to use a modified version of it. Yeah. Then this last question here, you know, I wasn't sure what I was going to do about this one. You know, how easy I was going to make it or how difficult I was going to make it, you know. But one of the things is, you know, if it's open book, then you're allowed to use everything, you know. So if you do search or look through the book or look at the index of the book, there's seawaters in the book. There's a whole section on seawater 16-5. And so we need a little bit more information to solve this, and we need the density of seawater. You could have assumed, you know, there are different ways you could have handled this. I mean, if you didn't find this, you could have made an assumption. For example, the swimming pool water had a density of 1, but seawater is probably more dense. But the chlorinating solution, which was highly dense, only had a density of 1.1. And so you'd expect seawater to have a density between 1 and 1.1. And so you could have guessed it and just used 1 sig fig, you know. If you use 1 sig fig, for example, you know, that would be easily within the range. So for example, if we use 1 sig fig, like say, okay, the density of seawater is 1 gram per milliliter, then that's anywhere from 0.5 to 1.4 grams per milliliter. Now, if we look at the density of different things, like 0.5 would be like wood. I mean, let's take a look at our book at the density here, you know, and see what some reasonable densities are. And so I just need to bring this up here. And then we can kind of estimate it based on other observations. This is the thing about, you know, it's not just memorization, it's being able to apply the observations. So we don't memorize. So the density of this is this, the density of that is that, but we try to see, you know, the patterns and trends within that. Should be more powerful. And so it was in chapter 3, I think. Let's see, not this one probably. So, you know, one of the things you could have done is you could have looked at some densities here, like pine wood is 0.5, seawater is definitely more dense than that. Water is 1.0. Glass is 2.5 times more dense. And so there's no way seawater is as dense as glass. I mean, if you drop a glass bottle in the ocean, it's going to sink. unless it's filled with air, you know, the glass in the bottle. If it's filled with air, then you have to account for the total volume. So there's a lot of air and glass. But if it's solid glass, forget it. It's going to sink, you know, and it's going to sink kind of like a rock. Basically, it is, you know. Glass is mostly made up of silicon dioxide, which is quartz, you know. But they put other chemicals into it. It's not pure quartz, and so it drops. Aluminum is 2.7, iron 7.8. And so, you know, seawater is going to be around 1. And like the chlorinating solution, you may guess that the chlorinating solution has to be dense. It has to be concentrated. Otherwise, you have to dump in way too much chlorinating solution, you know, in order to chlorinate your pool. So my guess is seawater is between 1.0 and 1.1. And so alternatively, we could have done that. You know, we could have guessed density for seawater between 1.0 and 1.1, you know, in that range. And then we could have calculated if it were 1.0, how many cubic miles would you need? If it were 1.1, how many cubic miles would you need? And then it would be between those two extremes. And so this is how you would answer a question like this. If you didn't have enough information, but you have some patterns, some trends, you know, not necessarily information that was memorized. I screwed this problem up because that wasn't my original intention for this problem. My original intention wasn't to make it a little bit harder like this. This is typical. You know, as a student, I hated take-home exams. They were the worst. The take-home exams, every take-home exam I took at UCLA and every take-home exam at UCSB I took was horrendously difficult. That is, you know, you spend all your time on the take-home exam to the neglect of every single other class you're doing, you know. Because, you know, they are purposely made because take-home exams, you could use anything you wanted, you know, any book, any internet source. So of course they have to make it hard. Otherwise, you know, if you could just find the answer and look it up, it's way too easy. You don't even have to think. So I hated take-home exams, but if I give a take-home exam, I got to make it a little bit challenging. So this would be, you know, a step up in challenge where, you know, this was a minor step up where you have to look up in the book. You know, I didn't tell you. I did say it was open book, but I didn't tell you. Information's there. But it might not have been in the book. If it wasn't in the book, then this would be the next level up. The next level up is you'd have to come up with a reasonable, you know, because if you don't know what the number is, you don't have it memorized. I don't think anybody has it memorized. You have to come up with some kind of reasonable density for the seawater, you know. Or I think I got comments about this, you know, about this. Actually, the intention was using conversion factors that we used in class. What I meant by that were, you know, the cubics, like these. Like you could find the conversion from, for example, cubic inches to cubic miles on Google. You could Google that. But I wanted to see the individual steps here. Now, this conversion factor, you know, where, you know, the density of seawater is 1.0 grams per milliliter. That one, that was fair use. You could have looked that up. You know, if we Googled it, I would have been fine. So if you did Google it, you know, yeah, that's not a problem. Seawater density. In fact, that's what I was expecting. I was expecting people to Google it. And you can see, you know, the temperature of the ocean varies, and the density of seawater varies with temperature. And so the temperature of the ocean varies, it says, about 20 degrees C from surface to bottom. And so the density varies from 1.024 to 1.0273. And so it's not a huge difference here in density. So about 1.03, maybe 1.02. And so between 1.02 and 1.03. And so what you could do is you could calculate, you know, the volume. You don't know the volumes, but we can kind of calculate just roughly what it is. To 2 sig figs, it's just 1.0. So that's why the book just uses 1.0. But to 3 sig figs, it would be 1.02 here. And the warmer water and the colder water would be at 1.03. So we could use like a mid value, or we could do a range, you know. We could do two calculations, one calculation of 1.02, one calculation of 1.03. You know, it's only 1% difference between those two. It's not huge. Or, you know, if this is using a more precise, more accurate density. If we just use 1.0, then we're about, you know, 2 to 3% off. You know, if you count this as 100, you know, this would be 2 out of 100, and this would be about 3 out of 100, you know, parts off. Let's see, water. Yeah, that's from Royal Institute of Chemistry, it looks like. This is from Wikipedia. This is Wikipedia say about seawater. Yeah. So the intention wasn't meant to make it too hard, you know, where you're going to look at the trends and you're going to come up with a reasonable estimate, that kind of thing. You know, either look it up in the book here or from some other source. Or, you know, you might think, well, seawater, you know, yeah, it's a little salty, but it's not like, you know, it's not like pickling water where it's really, really salty. You know, there's some salts in there. All right, so this was dimensional analysis here. Okay, so that's it. And then be careful, you know, subscripts and superscripts. You know, it was hard to tell for some people, you know, is that a subscript or superscript? It wasn't clear. You have to make sure it's clear. You know, for the most part, I gave people the benefit of the doubt, you know, but sometimes they weren't consistent. So, you know, if I was, okay, I'll assume that's a subscript, and then all of a sudden it's supposed to be a superscript, and it looks exactly the same, then I deducted that. All right, so that's a key. And like I said, I'll give you your exams back tomorrow. I'll send them back, the graded ones. I gotta scan them in, so finish them. All right, so today, like I said, I want to, because I'm behind a bit, so I don't want to rush too much. So let me go through this. Today's lab, so the first lab is really short, the burner lab. And so I want to just go through chapter 11 here. Atomic theory and quantum mechanics. Now we were looking at quantum theory, and so let's break down the development of quantum theory. Quantum theory started with the unusual light patterns. You know, these are the examples of the unusual light patterns here. And so quantum theory started with observations. And these observations couldn't be explained by classical physics. Classical physics predicted a continuous spectrum. This is a continuous spectrum. Continuous spectrum means we see all colors of light here. This is emission of light. And so this would be a light bulb or the sunlight, whatever. The sun is made up of hydrogen. So if we do, you know, hydrogen and make a light bulb out of that, we don't get, actually, this is not hydrogen. Hydrogen is this one, only 4 lines. This looks like some other element. So this is some other element or mix, you know, if we had hydrogen and mercury, we'd have all these together, or hydrogen, mercury, and neon. You just have one spectrum containing all these lines here. And so we could figure out, in fact, this is how they figure out what elements are out in the universe. You know, they look at the spectrum of those, either the emission spectrum like this, or the absorption spectrum like this. Absorption spectrum is when you shine all colors of light on a sample and see what colors it absorbs. And those end up being black here. And so we have these light patterns that were the observations. And then, yeah, we see the patterns, a mathematical pattern. And that mathematical pattern we can get as a law, is the Rydberg law. The Rydberg law, you know, is just an equation. The equation was that the energy of the line, the light here, the energy of that light corresponded to the Rydberg constant. minus r sub h, or the negative of the Rydberg constant, 1 over n final squared minus 1 over n initial squared. So this is a mathematical equation that you can plug in. So I'm sorry, if n final is 2, then we can explain all the lines in hydrogen here. And so this worked for hydrogen. So that was the law. And then we come up with some kind of hypothesis. The hypothesis is that energy is quantized. Energy is quantized. What that means is it's not continuous. Not continuous. And so here the energy is continuous. We have all the colors of the rainbow. Here the energy is quantized. That is, when it's quantized, there are forbidden energies and there's allowed energies. Here, forbidden energies and allowed energies. Same thing here, forbidden, but these are different forbidden and different allowed energies that we see here. And then the same thing here. And so energy is quantized with the hypothesis. Then, what does the formula say? This formula, after E, it's minus R sub H, R, capital R sub H. And then 1 over n. This formula, don't worry about it. It's just a law that explains this. This is for hydrogen. And then we come up with a theory here. The theory should be more fundamental, you know. And so the first theory that came up was Bohr theory. But Bohr theory, you know, electron orbits. This is Bohr theory. But it turned out Bohr was wrong. Bohr was wrong because it couldn't predict anything new. And so eventually this theory had to be modified. And this theory evolved into quantum theory. Quantum theory. You know, there are some important developments here that led to quantum theory, which we'll talk about. The important developments are from de Broglie, Heisenberg, and those led to quantum theory with Schrodinger. We'll talk about. We're going to talk about this timeline here. Okay, let's move on here. So to better understand this, we need to better understand light or electromagnetic radiation. There's lots of different types of light: gamma rays, radio waves, energy. The light's going to be characterized by 3 things that we are interested in light. You know, we're interested in, the what we call lambda, or the wavelength. I talked about wavelength, this peak to peak. This would be long wavelength here. This is short wavelength. Yeah. So that's lambda, the Greek letter, lowercase. And then we have the Greek letter nu, N-U. Nu is the frequency. So, you know, how frequently are these peaks hitting you? So if this wave is traveling here, this is going to be a little lower frequency. You know, it'll be boom, boom. This one will be at a higher frequency, boom, 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 boom. You know, because the waves are just hitting you a lot faster. And so higher frequency. There's a relationship between lambda and nu. And this relationship is this. C is equal to lambda times nu. C is the speed of light. What does it say after E? Is the other one nu? Okay, this is nu here. So many span. This is lambda here. Lambda's wavelength, nu is frequency. They're inversely proportional. So for example, if I'm looking for lambda, lambda is equal to c over nu. So if the frequency, c is the speed of light. This is speed of light. Speed of light, which is a constant. Speed of light. And so if I'm at high frequency, I have a very small lambda. If I'm at a low frequency, that is nu is very low, small, then lambda is big. And the same thing, frequency is inversely proportional to wavelength here. And so in other words, the longer the wavelength, the lower the frequency. And so lambda goes up, frequency goes down here. Lambda goes down, frequency goes up. So this is going to be higher frequency. Now waves, water waves don't move at the speed of light. The speed of light's 3 × 10⁸ meters per second. You don't worry about it. So I don't think we're doing any calculations here. And so they're moving very fast. And the wavelengths range, you know, when we look at the wavelengths range from 10 to the 8 meters, you know, which is kilometers, many, many kilometers, right? And all the way down to 10 to the minus 16 meters, which is way smaller than an atom, you know. The wavelengths range are huge. But look at the frequencies. The frequencies are going to be from 1 hertz, which is 1 cycles per second, to 10 to the 24 hertz, which is incredibly fast. Now, light is not water waves like this. Light is oscillating electric and magnetic fields. And so we really focus, let's just focus on the electric field. If we focus on electric field, an oscillating electric field is like this, plus here, you know, minus, plus, minus. And so what you see is you see the charge of the field change, you know, plus, minus, like that. Like that. Okay, now energy, this is Einstein. Einstein came up with this. Energy is equal to h nu, which is equal to hc over lambda. And so the energy is going to be directly proportional to the frequency. And so in other words, the higher the frequency, the higher the energy of the light. And so things with a very high frequency, gamma rays, will have high energy. Things with lower frequency, like radio waves, will have lower energy. Now, they both move at the same speed. So gamma rays and radio waves move just as fast as each other, which is odd. You would think that these are moving a lot faster, but they aren't. They're moving at the same speed. They just pack more punch. Also, decreasing lambda, you know, the shorter the wavelength, you know, the higher the energy. And vice versa. High frequency, high energy. Exactly, Kazra. High frequency, high energy. That's what we got. And, Einstein came up with the idea, you know, of this, you know. One way of thinking about it is like radio waves are more like ping pong balls, you know, ping pong balls. And gamma rays are more like bullets, ping pong balls and bullets kind of thing. And so this came up with, this is kind of interesting here. Let's say you have this is part of Einstein's, you know, Einstein won the Nobel Prize for something called the photoelectric effect. You don't have to know this, photoelectric effect. And what can happen is, what do positive and negative oscillating fields like that interact with? They interact with electrons. And so let's say you're an electron in a metal. Electrons in metals are kind of loosely held because electrons you know, they can easily move through the metals. So electrons and metals are loosely held. And sometimes electrons and metals are called a sea of electrons, you know, because the sea of electrons can move wherever it wants, you know, in the metal itself. And so let's say you're some light like this, and it's oscillating, you know, electric and magnetic field. You're an electron. What charge is an electron? An electron is negatively charged. So when the field comes here, this is going plus minus, the electron is going to start oscillating with the field too. And so the electron starts oscillating like this. And if it starts oscillating too much, it can get ionized. It can get knocked off the atom, you know, if the energy of light is high enough. And so this led to the photoelectric effect. That is, you know, if you have a piece of metal that's easily ionized, like potassium metal here, you know, and we shine light on this, let's say we shine red light on this. And let's say we use a 100-watt red light bulb. If we use a 100-watt red light bulb, here, nothing happens. Nothing happens. However, let's use a 100-watt. Let's use a 100-watt green light bulb. What do you think? Hey, this is a 100-watt. This is 100-watt. What's going to happen here? They're both 100 watts. You know what a watt is? Maybe I should tell you what a watt is. A watt is equal to a joule of energy per second. And so this is 100 joules of red light per second. This is 100 joules of green light per second. And so both of them have the same energy. What do you predict will happen here? Well, green light has higher frequency, shorter wavelength. Red light has lower frequency, longer wavelength. But they're both 100 joules per second. But what happens here is when green light impinges on here, it knocks electrons off the surface of potassium, you know, an electron. Red light, it's not enough, you know, but green light is enough, and it knocks the electrons off. This is called the photoelectric effect. You know. Now, the situation here is yes, but this is like, okay, 100 pounds of ping pong balls versus 100 pounds of bullets. You know, the joules part is the same. The joules part is the same. And so it's 100 pounds of ping pong balls, and this is 100 pounds of lead bullets. So 100 pounds of lead bullets, you're going to have fewer of them. You know, maybe you'll just have a few of them, but they're going to pack a punch. 100 pounds of ping pong balls, it's the same weight, but the ping pong ball doesn't do it. And so that's the photoelectric effect. Yeah, C is the speed of light. Speed of light. Which is a constant, 2.998 times 10 to the 8 meters per second. That's what it is. And so when we visualize this, you know, this is like ping pong balls. This is like bullets. And so what we can do is we can have the same amount, you know, of joules. Let's say I had 100 joules of radio waves versus 100 joules of gamma rays. 100 joules of gamma rays, even though it's the same energy, is going to do a lot more damage. A lot more damage because, you know, it's just focused in a small particle. Does that make sense? Okay, great. And so what we're going to look at is how matter interacts with light. And so let's do that down here. Light and matter. Let's start off with low energy, like radio waves. Now, when we look at radio waves, what do radio waves do? Radio waves can excite electrons in metals. In the old days, they used to have these metal antennas, you pull up in the car. You know, the problem is these metal antennas would break off. Somebody would accidentally break it off. And so people would, well, they didn't want to buy another antenna because they're kind of expensive. So, you know, they'd use a clothes hanger. They'd use a metal clothes hanger and jam it in there. So in the old days, you could see a lot of people driving around with a metal coat hanger stuck where their antenna should be, because radio waves are going to excite electrons and metals. Of course, you can't use plastic or wood hangers in there because, you know, the electrons aren't so loosely held in plastic. Electrons are tightly held in plastic and wood also, you know, more tightly held than in metals. Metals are loosely held. And so radio waves can excite electrons and metals. You know, microwaves can rotate molecules like water. Small molecules, rotate small molecules. And so like your microwave oven can rotate, it's enough energy to rotate, you know, and water molecules have a negative end and a positive end. And when the microwaves come, they can interact with that and cause the molecules to rotate. The microwave rotates small molecules. Infrared, IR, infrared, can cause vibrations. Like, for example, infrared lamps. Infrared lamps, you know, there's bonds, there's atoms, and it can cause those atoms to start vibrating. Infrared radiation. And when things start to vibrate and rotate, you know, kinetic energy goes up. You can cook food that way. So we can cook food with microwaves and infrared. Visible light excites electrons in matter. When I say excite, yeah, it just gets excited like this, but it doesn't get knocked off. It gets knocked off with this ionization. So, for example, radio waves can excite electrons, but not knock them off. But what happens if you put a metal in a microwave? Have you ever put metal into a microwave? When you put metals into microwaves, electrons get way too excited. And they can start, yeah, it kind of explodes. There's a whole bunch of sparks because the electrons and metals are getting way too excited. They're getting ionized. And so you don't want to put metals into microwave. It's too much energy. And, well, visible excites electrons in matter. Visible can also ionize, like green light can ionize potassium. You have to protect potassium metal from light. Otherwise, it's going to turn into potassium ions, you know, decompose. There are lots of things we need to protect from light. We protect it from light by using like jars that aren't see-through, you know. Like if I have a glass like this, you know, visible light can pass right through it. Well, you need to, well, we have a brown jar or an amber jar or a opaque jar that blocks out the light. So it doesn't decompose. But visible light excites electrons in matter. That's what causes the colors, you know. The colors of things are caused by, you know, visible light exciting electrons in matter. Ultraviolet breaks bonds. You know, this is why ultraviolet is bad. Breaks bonds. Covalent bonds, breaks bonds. X-rays and gamma rays are what we call ionizing radiation. You know, X-rays and gamma, this is the Greek letter gamma, lowercase. And we call these ionizing. Ionizing means they'll knock electrons off of matter and create ions, which is bad, you know, if you don't want it. Ionizing radiation. I mean, visible will ionize potassium. This is called ionizing potassium. You know, Einstein came up with this idea, you know, even though this is 100 joules and this is 100 joules, there's a difference in punch packs. The punch packs are called photons. So a photon of green light packs way more punch than a photon of red light. And so he came up with the idea of photons, light. And so green light would have powerful photons, red light would have soft photons and lots of them. Green light would have hard, fast protons, dense. That's kind of one way of visualizing it. Not exactly. Okay, so that's light and matter. Okay, let's move on. So, you know, the hypothesis of why we don't get a continuous spectrum, you know, we should get a continuous spectrum, but why we get this? This is called a line spectrum. This is a continuous spectrum. This is a line spectrum. I took from some website, examfear.com, but this looked pretty decent. So line spectrum. It's called a line spectrum, obviously, because it's got a bunch of lines there. This is also called line spectrum. And so we're looking at line spectra, spectra is plural, versus continuous spectrum here. You know, so we have two types of spectra, emission and absorption, like I said before. And if you have a continuum, you're allowed a continuum of energy. So this is gravitational energy. This is called a continuum here. This person can get any kind of gravitational potential energy they want, you know, a little bit higher, a little bit higher, a little bit higher, a lot higher, whatever. There's no forbidden. Nothing's forbidden here as far as height goes, you know. There's no forbidden height. All heights are allowed. And so we have a continuum of heights allowed. Continuum of heights allowed. When we have a continuum of heights allowed, then we have a continuum of energies, because gravitational potential energy, you know, gravitational potential energies, mgh. And so H is an important thing. This is for gravity. Here, they're forbidden energies, gravitational energies, because here it's stepped. And so this would be quantized here. This is a continuum. This is quantized. Quantized. All quantized is they're forbidden and they're allowed, you know. And so quantized energies here. Quantization, I should say quantization of H. Quantized H, I'll just say. And so the height is quantized. And so we could be one step up, two steps up, but can we be 1.5 steps? No, 1.5 steps is forbidden. This person can't stand at 1.5 steps. What about 1.1 steps? No, forbidden. What about 0.9 steps? Forbidden. 0.5 steps? Forbidden. All those are forbidden. And so the only ones that are allowed are the first step, the second step, the third step. And so it's quantized, 1, 2, 3, but nothing in between. Everything else is forbidden. Well, that's the thinking here. You know, this guy here is Max Planck, P-L-N-K, Max Planck. He was a physicist. Spell Planck right? Planck is his name. And, you know, he came up with this idea, quantized energy. And so this would be like a continuum of energies here. This is a continuum of energies that are allowed, like this. And so anything in this gray zone is allowed, versus quantized, where we're going to have these steps. And in between the steps is forbidden. You know, in between the steps is forbidden. And so each step that's shown here, in other words, forbidden. Each step that's shown here, each black line, this black line is allowed. And so only here. So if you're a person, you can be here, then you got to step up to here. There's no place to step in between. That's kind of weird because why is electron, why can't the electron go any speed it wants in an atom, But anyway, this explains. And so if we quantize energy, then pretty much that explains the Rydberg equation. The Rydberg equation is this. It's minus R sub H 1 over N final squared minus 1 over N initial squared. And so this would be final squared, initial squared. Now, the only way to get the Rydberg equation to work is if N is equal to 1, 2, 3, etc. It has to be an integer. We can't have 0.5, you can't have 1.1. It has to be 1, 2, 3. It has to occur in steps like this. And then this equation fits the line spectrum for hydrogen. And it works. You do not need to know the photoelectric effect. Photoelectric effect isn't even discussed in our book. Your book has lots of photos like this, so I thought it appropriate to put Einstein's photo and the photoelectric effect in there. But don't worry about the photoelectric effect at all. All my annotations are off. Otherwise, I'd write something there. Don't worry about the photoelectric effect. Just know that, Einstein kind of visualized energies occurring in packets. And so you could have high energy packets like bullets, or you could have low energy packets like ping pong balls, And so low energy light has like ping pong ball packets, and gamma rays have bullets packets, even though you can have the same total energy, This is kind of weird because I told you that red light won't ionize. Won't ionize, but surely, but that was only 100 watts. What if I went to 1,000 watts? If I went to 1,000 watts, yeah, it's the same thing. Rather than 100 pounds of ping pong balls, you have 1,000 pounds of ping pong balls falling, and none of them are going to do anything. And so even if you went up to 1,000 watts of red light, nothing happens, to the potassium. It'll get hot. Of course, it'll get hot, but you aren't going to be ionizing. And what if you went down from 100 watts of green light to 10 watts? Well, 10 watts are still going to ionize, just fewer electrons. And so that's the whole point of the photoelectric effect. And so we have two energies. Einstein, there's two energies. There's the total energy. You add up all the ping pong balls, you add up all the bullets. That's the total energy. And then you have the energy of the photon. And so the energy of the photon is what we're talking about here. These photons, gamma ray photons, pack a lot of energy. One gamma ray photon. What would you rather be hit with? One gamma ray photon or a million radio wave photons? I'd rather be hit with a million radio wave photons than one gamma ray photon, much more so. Even though a million radio wave photons might have more energy, total energy, than one gamma ray photon does. Okay, that's the photoelectric effect. I was listening to, the Fukushima thing. They had the meltdown there at the nuclear power plant, and people were playing. When politics and gets mixed with science, it's not good. Because people make things sound scientific. Like people were saying, oh yeah, the amount of radiation is like taking an airplane flight. Well, that's true. There's a lot of exposure to radiation there, but there are other factors there. Or the amount of radiation, what they're doing is they're taking that one gamma ray photon and distributing over the entire body. And when you do that, then there's no problem. But the gamma ray photon doesn't distribute over the entire body. The gamma ray photon hits, could hit a strand of DNA, cause a mutation, that kind of stuff. And so people play with numbers to suit their, their particular agenda, to make things sound worse or to make things sound better sometimes. But anyway, and so people were playing with total energy and photon energy and mixing the two to suit their particular point of view. Anyway, let's move on to this here. So, okay, energy is quantized. Now, how do we visualize what's happening in the atom? How we visualize what's happening in the atom is via the Bohr theory, or the Bohr model, or the Bohr hypothesis. This Bohr hypothesis developed into the theory, and then the theory had to be modified. But Bohr pictured this. There's a nucleus, and then there are electrons that orbit around the nucleus in orbits like this. These are called planar orbits, like planets, like that. And so they can be in any plane here. Well, let's flatten them out like this. Flatten them out. They don't have to be flattened out like this. They can be like this. But if we flatten them out, then we're going to see different orbits. These are what we call the allowed orbits for the electron. Now, why are certain orbits allowed and certain orbits forbidden? And so, for example, here, the n equals 1 is the first allowed orbit. And the n equals 1 orbit is going to have a radius. This is angstroms here. 10 to the minus 10 meters is defined as an angstrom. Here. And so the first allowed orbit here is at 0.5292 angstroms, which is 52.92 picometers. That's the radius of the first orbit there. Now, let's say it doesn't want to orbit there. Let's say it wants to orbit at 5293 or 5294. Well, no, it can't, because those are forbidden. Let's say it wants to orbit at 5291. Can it? No, it can't, because that's forbidden. In fact, this is the only allowed one here. So it can't be any closer and it can't be any further. This is it. And this is the lowest energy orbit it can have. There are higher energy orbits. As it gets further away, it has to have more energy. And so the next orbit is at 2.1168 angstroms, which is, 211.68 picometers. And so that's the next one. And so the weird thing is this electron can't not orbit here. It has to jump to this next orbit here. It can't, it can't be between this. And so if it jumps from the first orbit to the second orbit, that would be like this. The energy, we can figure out the energy from physics. The energy of the first orbit this is all relative. The zero, it makes no sense for a negative energy. Zero means this is zero. Zero's at the top. Zero means the electron's no longer with it. The electron is ionized. And so when we're at zero energy, the electron's ionized. So you take the nucleus and you pull apart the electron, that's zero energy. As you bring the electron closer to the nucleus, the energy goes down because it's positive, negative. Positive, negative is favorable, and so the energy goes down. And so that's why the energy is negative. It's sinking down in this well from being totally separated. It's like trying to pull apart two things that like each other. If you try to pull two things that like each other apart, it's going to require energy. And so let's separate them infinitely far apart. We're going to call that zero. And then let them come closer together, the energy is going to go down. And so if we map out all these orbits in terms of energy, we get something called an energy level diagram. And so the n equals 1 orbit has this energy, which is minus 2.179 joules, but they rounded it here. You can see it's minus 2.18 barely. And we call that the ground state. The ground state is the lowest energy. So if the electron's down here, it's in the ground state. It's happy. Now, the next orbit is up here. Now, these orbits aren't drawn. The orbits get bigger and bigger. It's not drawn to scale because this one's only half an angstrom. This is 2 angstroms. This is 4 angstroms, but the next one's 8 angstroms, which means it should be out here. And so this is not drawn to scale. The orbits actually, the energies converge. Interestingly, you can see the energies are going to start to converge, but the orbits diverge. And so the orbit goes like this. The orbits just get farther and farther out. The energies are going to kind of converge here. And so Bohr hypothesized this and turned into the Bohr theory, in which the electrons orbit in their allowed orbits and forbidden orbits. You know, everything in between is forbidden. And the forbidden orbits, you know, why are they forbidden? Well, there's no answer to that. It's just what's observed. You know, it's forbidden, it's forbidden. That's called a postulate. You know, it's just postulated. You accept it without proof. There's no proof. Well, there is proof because it's not observed, all this blacked out area here. And so for hydrogen, the lines are a result of this. We can think of these as floors here, like the first orbit is the first floor, the second orbit here is the second floor, and it's quite a bit higher in energy. Yeah, here, minus 0.5. You see how the gaps here, we go from -2 to -0.5, -0.5, -0.24. The gaps get smaller and smaller in terms of energy, but the radii get bigger and bigger. And so the gaps get smaller and smaller. You can see the gaps get smaller and smaller, and pretty soon they're infinitesimally small. They're an infinite number of orbits. You know, this goes all the way to n equals infinity. When n equals infinity, then the electron's infinitely far away, and the energy is 0. And so the radius is equal to infinity, or approaches infinity, and the energy goes to 0. It goes to 0 because it's just arbitrarily defined. You know, obviously there's energy there. It's just arbitrarily defined as 0. And that's what the 0 is here. All right, so the electron can hop up or hop down. Well, what causes it to hop up? Collisions, energy, kinetic energy, light, you know, things cause it to pop up here. And it could absorb a lot of energy, or it could absorb a little bit of energy, you know. If it absorbs too much energy, then it gets knocked off. It's called ionization. If it absorbs too much energy, it gets knocked off all the way up to n equals infinity here. It's not hard to do. You know, we can ionize hydrogen easily to make H+. Now, the lines that result in the line spectrum here are caused by this: electrons being excited to the 3rd floor, electrons being excited to the 4th floor, the 5th floor, and the 6th floor. And when an electron's excited to the 3rd floor, it doesn't have to drop all the way down to the 1st floor. When an electron's in the 3rd floor, it could drop to the 2nd floor. And so if I have an electron that's on the 3rd floor that drops to the 2nd floor, that gives me the red light here. And so here's the 3rd floor. So the electron's on the 3rd floor, it drops down to the 2nd floor. It gives me the red light. If an electron is on the 4th floor and drops down to the 2nd floor, it's a bigger drop. And so it gives me the green light here. If an electron's on the 5th floor and drops to the 2nd floor, it gives me the blue light. And finally, if an electron is on the 6th floor and drops to the 2nd floor, it gives me the violet light here. But what happens if an electron is on the 7th floor and drops to the 2nd floor? Well, it goes beyond violet. What's beyond violet? What's beyond violet is ultraviolet, right? And so we don't see that happen because ultraviolet's invisible, but if we have a special ultraviolet detector, we'll see it. And so even though we don't see ultraviolet, there are a whole bunch of lines in the ultraviolet. These are called the Lyman series. And there are a whole bunch of lines in the infrared. These are called the Paschen series. And the visible is called the Balmer series. And so this was the success of the Bohr. The Bohr, we could use the Rydberg equation to calculate all these lines, whether they're in the visible or the invisible. And then all these lines were discovered. Lyman discovered the UV lines. Paschen discovered the infrared lines, and Balmer discovered the visible lines here. Visible lines were discovered well before the theory, though, that came up. This is Bohr, Niels Bohr here. Unfortunately for Niels Bohr, you know, a theory should do two things. A theory should do what? Two things. A theory is supposed to be doing two things. What are the two things a theory is supposed to do? The recall is a bit slow. Theory we talked about on day one. So right now, you know, it's week 3. So you should have, this should be like the kindergarten material of Chem 4. You know, the kindergarten material of Chem 4 is the stuff you do on day 1. But now you should have seen it so many times. It should be so routinely easy. Like, you know, it's like you let's say you learned how to ride a bicycle in kindergarten. Now you're in college. You know, well, riding a bicycle should be pretty straightforward. That's what your goal is, you know. And trust me, there are lots of people who want to get into medical school. When I was at UCSB, I was a teaching assistant there. There's a class of 300 Chem 1A students. Professor asked, how many of you are going or planning to go to medical school? And like 80% of the class raised their hand. Well, are there enough spaces for those students to go to medical school? Oh, no, not at all. And so all those students know that, you know, they're not naive. They know that the competition's intense. And so they work incredibly hard to make sure that they have the one up on all of the other 80% of the students in that course, because all of them had the dream of going to medical school since who knows when, you know. And so be aware that, you know, things in the sciences can get kind of cutthroat. You know, people are going to be really on top of it because, you know, that's been their lifelong goal, and they're going to do whatever it takes to get in. And they're going to blow out the curve. You know, blowing out the curve means that you don't want to be stuck at the tail end of the curve. If you're stuck at the tail end of the curve, that's the DF range. Lots of people get stuck back there. And so all those medical, pre-meds, they call them, all those pre-meds don't want an A. They want the top score in the class. That's how they're going to stand out. It's not just getting an A. They want the top. They want to be at the top, or at least the top 5, you know, something like that. So, so think about that. You know, if your goal is medical, then you got to get on it now. You know, because the competition is very intense. And I know there are people, but you know, not everybody's into that. You know, I wasn't, and so. But now's the time to get on it. You know, otherwise you're already behind. And so, hey, let's go on here because I know some people they do want to go to medical school. So make sure you don't fall in the middle or the tail. Okay. It's break time? Yeah, it's break time. All right, so let's take a break, and hopefully by the end of the break, you can tell me. It should be such a simple question, so maybe still too early to get the blood flowing, but you know, it shouldn't be. That should be such a simple question, so I'll be surprised if no one can answer it. Okay, I'll pause the recording now. Okay, so we're back. Did somebody, Kazra, you say accepted fundamental description? Yes. The exceptions part, no. It's just accepted fundamental descriptions. You don't need exceptions there with exceptions. There might be, but if there are too many exceptions in the theory, then it's not a very good theory. What's the other thing? That's number 1. What's number 2? Oh, so that tells me 2 things. Yeah. 1 is a lot of people aren't reviewing their notes, or 2, your notes are incomplete, you know, and therefore you don't even know what you're missing. Francis, that's correct. Predict new observations. So that was the failing of the Bohr theory. The failing of the Bohr theory is it failed to predict. It was able to predict this, but the Bohr failed to predict anything else. And so Bohr theory could not predict beyond hydrogen. And let me put a little asterisk here, and other one electron species. One electron species. And so a theory should be able to do two things. A theory should be able to provide a fundamental explanation of what's going on, or description. This is the fundamental description of what's going on in the line spectrum. However, it failed number two. And that's good, Francis. I'm glad you got that. And that is, it couldn't predict. And so the next most complicated atom is helium. And helium is not here, but hydrogen, is fine, but helium fails. When you try to apply this to helium, he couldn't predict the lines. And so something was wrong with the Bohr theory. And so the Bohr theory had to change or evolve because, in other words, Bohr theory is abandoned. It was abandoned, but not everything. This is why Bohr is still relevant. Not everything about the theory was abandoned. The whole idea of quantization was retained. And so quantum mechanics came about through some major developments. First one is this person here. This person is de Broglie. Oops, go there. De Broglie. And de Broglie came up with the idea of wave-particle duality. Wave-particle duality. The main impact it had is, well, there was already wave-particle duality from Einstein. A photon of light is kind of like a particle of light, but it doesn't have any mass. It doesn't have any rest mass. And so light, it has like particle-like characteristics. Like this is what I was saying, ping pong balls versus bullets, they're particle-like characteristics. It's not just waves like this, The same thing with electrons. Electrons are particles, but they have wave characteristics. And so electron has both particle and wave characteristics. An electron is very tricky to explain because is it a wave? Is it a particle? What is it? Well, it's neither. And so electrons tricky to explain unless you get into the latest particle physics, from the Large Hadron Collider and that team of physicists, how they envision things, the Higgs particle, etc. And so when you get into Higgs and that kind of stuff, then it makes a lot more sense, what an electron is. But for us, an electron has both. So on the one hand, it's like a particle, the mass. On the other hand, it's like a wave, like light. It has both particle and light-like properties. Wave properties. So electrons have wavelengths, This wasn't noticed before because the wavelengths are extremely small. Not noticed before. The wavelength is extremely small. Like this. And so when we look at a baseball has wave properties too, but you can throw a baseball any speed you want. And this is why it was not noticed before, because the electron wasn't confined to such a small space. Let's say when we're looking at an electron in the sun, the electron in the sun can have any energy it wants. There are no forbidden energies, because the electron's free to roam a huge space. It would be like a killer whale. You know, a killer whale, can it swim any speed it wants, you know, up to its maximum speed in the open ocean? Yeah. A killer whale is not constrained. You know, a killer whale can go as fast as it wants in the open ocean. But what happens to, let's say, a killer whale at SeaWorld? You know, a killer whale at SeaWorld, can it go any speed it wants? No, all of a sudden that killer whale is confined to a small tank. And now it can't go any speed it wants. It has to only go certain speeds. Maybe it gets one kick out of its tail and then turns around and gets another kick out of the tail, or maybe two kicks out of the tail. Well, that's what happens. When an electron is in a big open space, then this wavelength is irrelevant, you know, pretty much. I mean, it's relevant, but its relevance is negligible. However, when an electron is confined to a tiny space, then that wavelength is relevant. This is like the killer whale, you know. And you confine that electron to a tiny space, then it makes a difference, you know, about how or what energies are allowed. And so for de Broglie, the biggest thing we have is something called standing waves. And I forgot to insert a drawing of standing waves here. But let's take a look at standing waves. The spelling is so bad here. So when waves are confined to a small space, this is what happens. Like on a musical instrument. Let me get some decent ones here. All right, maybe this one will serve purposes here. No, it won't. This is standing waves in musical instruments. So when you pluck a musical instrument, like a guitar string or something like that, the lowest energy you can have is this. This is called a half wavelength. And so we could fit a half wavelength in there. That's the lowest. We can't fit like a quarter wavelength because the string's not attached up here. The string's attached here and here. And so when you pluck it, you can get this sound. If you pluck it harder, then you can fit a full wavelength there. That would be called the second harmonic, the fundamental first harmonic here, or the first overtone here. If you pluck it even harder, you can fit 3 half wavelengths in there. And if you plug it even harder, you could fit 4 half wavelengths in there. And so this is quantized in terms of half wavelengths, you know, 1/2 lambda or lambda over 2. And so we can see that musical instruments are naturally quantized here by n times lambda over 2, where n is equal to 1. And so we have 1/2 wavelength. You know, n equals 2, so we have 2 half wavelengths. N equals 3, 3 half wavelengths. N equals 4, it's 4 half wavelengths, like that. And this is a small space. Small space. Let's make it a huge space. So take your string and then put one end in Torrance, and you put the other end in Irvine. So if you have a string like that long, you know, how many half wavelengths can you fit in there, you know? And pretty soon what happens is when the electron, let's say you're the electron, right? And so your electron, you're the killer whale. And so you could do this, or you could do this, you know, things are getting tight in this tight pool. But if you're the electron in the sun, you know, the sun is so huge and the wavelength is so small that let's say here we have 1 trillion half wavelengths. And then let's say the next energy up would be 1 trillion and 1 half wavelengths. Can you notice the difference in sound between having 1 trillion half wavelengths and 1 trillion and 1 half wavelengths? Do you think you'd be able to detect the sound difference between 1 trillion half wavelengths and 1 trillion and 1 half wavelengths? No. And so this is why it's a continuum. It's a continuum in the sun because it's huge. And if you get a trillion or quadrillion half wavelengths in there, then the next allowed one would be +1. You know, the same thing in the metal. In the light bulb, we have an electron in tungsten metal. And so when we're looking at a light bulb, we have the tungsten filament here. And it's the same thing. You know, this tungsten is huge. This piece of wire is huge compared to the size of the electron. So we can fit lots of half wavelengths in there. And so tungsten light bulb or the sun gives us a continuum. But when we put it into an atom of hydrogen, this would be the H atom, then all of a sudden we have three-dimensional situation where we have the nucleus here and the electron has to have the right number of half wavelengths to fit around here. If it has too many or too few, we get something called destructive interference. That is, if the waves don't match, then they cancel each other out. And so let's say if I have a wave like this and they're mismatched, you know, then I get something called destructive interference where a peak of one wave cancels the valley of another wave and the wave cancels itself out. And so we got to make sure. So the next allowed energy here would be, okay, this is 1, 2, 3, 4 half wavelengths. The next allowed energy would be 5 half wavelengths in there. And so quantization occurs because we start confining the electron, which is a big fish, into a very small, very, very small pond, which is the atom. When the electron, the big fish, is confined to the open ocean, then we don't see this. And so this is why the classical physicists didn't notice this. They didn't notice this because they're working with huge ponds, open oceans. Whereas once we started getting to atoms, then you know, the quantum physicists started noticing these kinds of things. And you start noticing when you tried to build a hydrogen atom lamp, you know, the hydrogen atom lamp. The hydrogen atom lamp, you know, you think is a plasma, so there are free electrons there, but a lot of the electrons are still stuck on the hydrogen atom. That's what's giving these lines like this here. The number of free electrons, there are different kinds of plasmas. The sun plasma is called the thermal plasma. A hydrogen lamp or fluorescent lamp or neon light bulb is called a non-equilibrium plasma. There are different characteristics to those things. And so de Broglie, this is the important contribution of de Broglie. You just didn't notice it when, you know, if you got the killer whale in the open ocean, you don't notice, you know, that there are certain kicks of the tail, you know. It's only when you start to confine the killer whale, you know, how many kicks can it get to get across, you know, the pool. And it has to do full kicks. So with de Broglie, the wave particle duality, then it is, electrons naturally come quantized in atoms. Electrons in atoms have quantized energies. This person is Heisenberg. This is the real Heisenberg here. This is the other Heisenberg. This Heisenberg was named after this Heisenberg, but I don't know why. Because this Heisenberg is responsible for the Heisenberg uncertainty principle. And so, Heisenberg uncertainty principle is very famous. Heisenberg uncertainty principle says that the philosophy, philosophically, Heisenberg uncertainty principle says that we live in a non-deterministic world. The Bohr model was a deterministic world. The Bohr model, you could determine where the electron will be in any point in time. But Heisenberg was like okay, the Bohr model is like this. You have a proton here, and then you have this electron orbiting. So it's like a satellite. We can predict where that satellite's going to be at any time, and we can predict how fast it's going to be at any time. This is the Bohr model. And so the Bohr model is deterministic because we can determine two things that we want to determine. We want to determine its position and its energy or speed. Energy or speed. Do that. With Heisenberg, we can't. You can't determine these with high precision. Okay. Can't determine both position and actually in momentum. Momentum is energy, speed, all mixed together. Position and I better use what he did, momentum, which is another way of thinking about energy. It's mass times velocity, it's momentum. But you can't determine both position and momentum simultaneously with good accuracy. There's uncertainty together with precision or accuracy. I'll just say precision in this case. You could determine one or the other. And so for us, the end result is this. For us, we determine energy with precision, high precision, but the position will be very low precision. In other words, the position will be uncertain, but position will contain uncertainty. We can determine the position with certainty, but that means the energy is uncertain. And so the way to think about the Heisenberg uncertainty principle is like a bird. Let's say you have a low energy bird. And so we know it's a low energy bird. You have a low energy bird, here's the bird nest. Is it a deterministic world? Can you predict where that bird is going to be in 5 minutes? No, it might be here. But we do know it's low energy, so it can't go too far. So it might be here. Here. Actually, let's use this. So let's say the nest is in the center. The electron's the bird. It might be here. It might be here. Each dot represents where the bird was last seen. And then over a long period of time, you'll see, well, that bird doesn't have too much energy, so it can't go too far. So the dots start to level off. In fact, if you look at this ring contains 90 or 95% of the dots. 5% of the dots lie outside. And so the bird's probably not going to be that far away. But there's a tiny probability that the bird might actually be way out there, you know, tiny probability, but it's there. But pretty much there's 95% probability it's going to be within this ring here, because 95% of the dots are within the ring. But at any point in time, like 5 minutes later, let's say we see the bird here. Can you tell me where it's going to be 5 minutes later? No. That's what I mean by uncertainty here. And therefore we do this. We know the energy with precision, but the position is given by probability. A probability map like this. This is a probability map. And so position is given by Heisenberg. Our end result for Heisenberg is to say this. We know the energy, but the position is going to be given by probability. No position, I mean no energy. No energy. It's a trade-off. We could trade off one for the other, or we can compromise both. But position, no energy, but position is given by probability. Okay. Better write in all caps, probably. And so this is the Bohr model. Bohr model is very deterministic. We know where the electrons are, and if we know what it's traveling, you know, it's like a satellite. We just track it. You know the position of the satellite at any time. Whereas because of Heisenberg, we have to visualize it like a bird, you know, and we come up with a probability map, you know. There's a probability map. The bird should be close to the nest, but it could be farther. But the probability goes down, and it can be way far, and probability goes way down. And so what that map looks like is a sphere, you know, the bird's going to be in this sphere here. And that's what we're going to get. And so if we take de Broglie and Heisenberg, then comes Schrodinger. This is Schrodinger. Schrodinger. And Schrodinger's equation is the equation of quantum mechanics. You know, he puts all these things together plus the physics. Physics, including quantized energy, wave properties, Heisenberg, wraps it up into an equation called the Schrodinger equation. The Schrodinger equation is the equation of quantum mechanics. The equation, the math of quantum mechanics. This Heisenberg, I don't know, probably everybody, does everybody know this Heisenberg? Or anyone not recognize this one? Yeah, this Heisenberg was a synthetic chemist, very good at making crystals of whatever it's making on the TV show. But okay, so we have quantum mechanics, which puts it, and so when we now visualize, so this is out, the Bohr model's out. Bohr model is out. Let me just X that out. The quantum mechanical model is in. Now, this is just one electron. This is one bird, so it's just one electron here. That's it. What about all the other electrons? What's happening if there are more electrons? And there are more electrons for bigger atoms. So what's happening with those? Let's take a look. So we need to come up with a distinction here. And the distinction is going to be this. This we call orbits. And orbits are wrong. But the problem is we call these orbitals. And so this whole thing of visualizing an electron as a bird is called an orbital, and this whole map, the probability map, is called an orbital, and the energy is called an orbital. We get orbitals, these come from the Schrodinger equation. The Schrodinger equation spits out orbitals. Orbitals are the allowed answers to the Schrodinger equation. Schrodinger equation. And so the Schrodinger equation tells us what's allowed for the electron, both in terms of energy and position. And so orbits are no more, orbitals, yes. Orbitals are quantum mechanics. Orbits are Bohr, and Bohr is no longer valid. So let's look at orbitals. Look at orbitals here. We'll map them out. So rather than showing all the dots, you know, where the bird is, we'll just draw a little boundary. And that boundary is 95% chance of finding the bird inside or the electron inside, about 5% chance of finding the electron outside. So this is the lowest energy. The lowest energy is called 1s. So this is low energy, it's not going to go very far. The next higher energy would be called a 2s. And so that's up here in energy. This is called an energy level diagram on the left here. Write that down. This is energy level diagram. And energy level diagram goes all the way up to infinity. Infinity is not infinitely far away in terms of energy because the energies start to converge. Here we go. Up. Energy level diagram. Here. And so the lowest energy electrons here in the 1s, and then it goes up 2s and 3s. And then there are different shapes to these. You know, it goes 2s to a 2p here that's higher in energy. They offset it because it's got a different shape to it. This is, an S looks like a ball, a sphere. A P looks like a dumbbell, like this. It's a P shape. Then there's D-shaped. This is D-shaped orbitals here. You know, where do these shapes come from? These shapes come from three-dimensional standing waves. Let's take a look at two-dimensional standing waves. Those are easy to visualize. We see quantization, like a two-dimensional standing wave would be like a drum. You know? There are forbidden sounds from a drum and allowed sounds from a drum. And so if we look at, let's look at 2D standing waves. 2D standing waves. Maybe videos. This is probably okay. So this is a plate with a whole bunch of powder on the plate. And this plate is going to be quantized also, the weight, because this plate is, this is like being a fish in the swimming pool, but it's going to be in 2 dimensions rather than 3 dimensions. And so how can the fish swim on this plate kind of deal? And so let's watch this here. Let's see. Okay, this is an allowed energy. Do you see there's going to be peaks and valleys in the wave. That's a 2-dimensional wave. And the sand's going to collect in the valleys. Forbidden, 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 allowed. You know, well, right Now that's allowed. So that's an allowed waveform. And then it goes forbidden, 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 allowed. Forbidden, allowed. Forbidden, 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 allowed. Forbidden, 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 allowed. Well, now it's forbidden. Now it's allowed. And so you can see that there are going to be allowed energies for the plate and forbidden. The forbidden ones, nothing happens to the plate. But when you hit a loud sound, then the plate starts to vibrate with that loud sound. And we get these two-dimensional waveforms like this. And so these are, this is quantization in 2 dimensions. And this is standing waves, like the guitar string or the string, the musical string that we have. Just looking at what sounds are allowed and forbidden. So, same thing here, you know, these are the waveforms, allowed, you know, allowed, allowed, allowed. We see.
If you blow air over the top of a soda bottle, you get a tone. I've got a soda bottle right here. I'm going to show you. Listen to this.
Here. Is it? We're still okay. All right, so we can map all these out. You know, with the Schrodinger equation, these are what we calculate for allowed. We have the 1s orbital is allowed, the 2s orbital, this is what a 2s orbital looks like, is allowed. The 2p orbitals are allowed, these are what p's look like. The 3s orbital is allowed, 3p's allowed, 4s allowed, 3d, 4p, 5s. These are all the allowed orbitals. Now, we want to be able to map this out. Now, how do we map this out? Well, the Schrodinger equation, what it spits out is it spits out other equations. And the other equations are going to depend on 4 variables. These 4 variables, they're mathematical restrictions for the allowed solutions to the Schrodinger equation. And this is it, mathematical restrictions to the answers to the Schrodinger equation. Well, for the hydrogen atom, how many are there? How many allowed orbitals are there? For the hydrogen, in fact, for any atom, there are an infinite number of answers. And so for each atom, there are an infinite number. There is an infinite number of allowed orbitals. Well, you might think, well, if there's an infinite number of allowed orbitals, and what's forbidden? Well, there's an infinite number of allowed orbitals, and there's an infinite number of forbidden orbitals. So it's weird. It's weird. Well, if there's an infinite number, how the heck do you figure them out? Well, the way to figure them out is there's mathematical restrictions, there's patterns. These mathematical restrictions are patterns for each atom. This is a mistake. It's supposed to be there. I don't know why. For each atom, there is an infinite number of allowed orbitals. These are restricted by mathematical patterns or mathematical equations. Mathematical restrictions allows one mathematical restrictions allows one to determine. We could determine these qualitatively very easily. And so we can figure it out, you know, what comes next, you know, what comes next, what comes next, what comes next. And what comes next is based on these quantum numbers, three quantum numbers. The first three quantum numbers here define the orbital. That pretty much tells us what orbital it is. The last quantum number is for the electron. So we'll talk about that last one. And so it's just the first three quantum numbers here. And so what are the mathematical restrictions to this? So let's go on here. So the mathematical restrictions, yeah, you're right. That's correct. There's for each atom. And so N tells us, you know, what floor we're on: first floor, second floor, third floor, kind of thing. This is called the principal energy. Principal. What was the second thing? Unfortunately, I deleted it. Somebody get it? Okay. Basically, they're infinite. This is going to go all the way to n equals infinity. And so what we're looking for is just mathematical patterns, you know, based on n, l, and m, n, l, and m sub l. Oh, yeah, mathematical restrictions allows one to determine, right? And so this is a principal quantum number. Principal quantum number. It's basically what floor, first floor is lowest energy. So it's the principal energy quantum number. You know, the energy is dictated on 1. So 1's the lowest energy we can have. And then the second floor, the third floor, the fourth floor, all the way up to the max. The max is infinity. And so we're going to go first, second, third, fourth, fifth, sixth, all the way to infinity. Well, that's a lot. It's a lot, but they start to converge up here. So it's not infinitely far away. We don't have to draw a chart that goes up an infinite distance because of that. This basically tells us the energy level. L is what we call the angular momentum quantum number. Angular momentum quantum number, Q number. I'll just do that. And L's going to start at 0. N does not start at 0. L starts at 0. It goes 1, 2. And then it's just going to go to a max of n minus 1. So the biggest L we can have is n minus 1. And it's going to take all values. This. Now, L tells us the shape of the orbital. The shape. So for example, when L is equal to 0, we get the S shape. When L is equal to 1, we get the P shape. When L is equal to 2, we get the D shape. When L equals 3, let me add that in here, we get the F shape. And then it goes kind of alphabetical after that. M sub L is the magnetic quantum number. Magnetic quantum number. And what M sub L tells us is the number and orientation of each L, number and orientation of each L. So what we're going to have is we're going to have 0, plus or minus 1, plus or minus 2, all the way up to a max of plus or minus L. And so I need to talk about these people here, but let's look at 1s. 1s, each orbital is represented by 3 quantum numbers, n, l, and m. And so 1s is a 1, 0, 0. When n equals 1, l equals 0. We can't have l equal 1. And m will be plus or minus 0 in this case, or just 0. And so this is NLM. And this is 1s orbital is equal to 1, 0, 0 orbital. Then we're done. That's it for n. But when n equals 2, we have more options. When n equals 2, then we have L equals 0 and 1. If n equals 2 and L equals 0, then we get 2, 0. And then m has got to be 0. So that's 2, 0, 0. This is 2, 1, negative 1. This is 2, 1, 0. This is 2, 1, 1. When n equals 3, then we have 3, 0, 0, 3, 1, negative 1, 3, 1, 0, 3, 1, 1. We also have 3, 2, 3, 2, negative 2, 3, 2, negative 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. When n equals 4, then we have 4, 0, 0. We have 4, 1, negative 1, 4, 1, 0, 4, 1, 1. We also have 4, 2, 4, 2, negative 2, 4, 2, negative 1, 4, 2, 0, 4, 2, 1, 4, 2, 2. We also have 4, 3, 4, 3, negative 3, 4, 3, negative 2, 4, 3, negative 1, 4, 3, 0, 4, 3, 1, 4, 3, 2, 4, 3, 3. We do not have 4, 4. 4, 4, we can't have an L equal to 4, the same as n. So 4, 4 doesn't exist. Then we go to 5, and we can go on. So we can build up the table like this table. Here's when L, this is the shape here. The number of orbitals is given by how many values we have. So when L is equal to 0, like 2, 0, 0, we only have 1 orbital. When L is equal to 1, we have 3 orbitals. Don't worry about calculating the numbers. We're just looking at the pattern right now. So don't worry about it yet. We'll get to it. Here we have 3 orbitals. You know, for 2p, when we have a p orbital, we have 3 of them. The negative 1, the 0, the 1. The negative 1, the 0, the 1. The negative 1, the 0, the 1. That's when we have p. When we have d, we have 5 of them. The negative 2, the negative 1, 0, 1, 2. Angular momentum quantum number. L is equal to angular momentum quantum number. The shape. L is equal to the shape. And so S shape, P shape, D shape, F shape. How many different P shapes are there? There are 3. They all look the same. They have different orientation. So let me go back here. All the P's look the same. They just have different orientations. Now the D's kind of look the same with different orientations except this one. This one's a bit different, but they're all, you know, there are 5 different D ones. The negative 2, the negative 1, the 0, the positive 1, and the 2. And so we're just looking at the pattern right now, just seeing the pattern. You know, that's it. So one thing is we got to generate the allowed orbitals. These are the allowed orbitals. And this is another pattern we see for the energies. If we build a pyramid like this, this is called off bow. It's off bow. off-bow principle. This is off-bow here. We also need some things here in addition to off-bow. This is filling the orbitals with electrons. And so over here, first we need to generate the orbitals, and then we're going to fill it. And so filling orbitals. We pay attention to these guys. This is poly. With poly, we have something called the Pauli exclusion principle. Pauli exclusion principle. Each of these orbitals can hold 2 electrons. 2 electrons max per orbital. The Pauli exclusion principle is a little bit more involved than that, but that's the basic result. And they have to be what we call opposite spin. We'll talk about that later. This is Hund's, or Hund. And we have something called Hund's rule. Hund's rule, which we'll talk about. And then we have the off-bow principle. Off-bow principle is the ranking of the energies, and we fill the lowest energy first to get the ground state. Off-bow principle. And so Pauli exclusion principle, Hund's rule, and off-bow principle is how we use this. First, we got to generate. How we generate it is by using the quantum numbers and the Schrodinger equation. These come out of the Schrodinger equation. The Schrodinger equation has an infinite number of answers, which is too much to memorize. So we break those into a pattern. This is a mathematical pattern that we see in the answers to the Schrodinger equation, and then we can generate this whole chart if we use the off-bow principle here. Help us. Now, the chemistry supplement, you know, has, our book doesn't go into it in this much detail. We have to look at the chemistry supplement to see it in this much detail. This is not the level of detail in Chem 1A, but it makes a better transition to Chem 1A. Because the level of detail in Chem 1A is much more. And so if you go to quantum in your supplement, then we can look at quantum numbers, you know, the mathematical restrictions to the answers to the Schrodinger equation, and electronic structure, the orbitals. We have the principal quantum number n, which we talked about. N has these mathematical restrictions. It's an integer from 1 to infinity. We have the azimuthal quantum number, or the angular momentum quantum number. You know, angular momentum and azimuthal quantum number are the same thing. These are mathematical restrictions on L, 0 up to a max of n minus 1, all values, takes on all values. So if n equals 4, then we have 3, 0, 1, and 2. And so this is what we can do here, just briefly. If n equals 4, then I'm going to have an S, so I'll have 4S. I'm going to have a P, so I'll have a 4P. I'll have a D, 4D, and I'll have an F, a 4F. So I expect to see a 4S, 4P, 4D, and 4F. I don't expect to see, well, after F comes G, A, B, C, D, F, G, G. I don't expect to see a 4G because I can only go to a max of n minus 1. Well, n's 4, the max is 3. And so 4f is the max. However, when I get to n equals 5, then a 5G orbital is possible according to the Schrodinger equation. So that's how we use these mathematical restrictions here. Otherwise, you know, how do you track an infinite number of answers without knowing some kind of pattern? And then we have the magnetic quantum number here, which varies from minus L to plus L going through 0. So minimum minus L to max plus L. This tells us the number and the orientation. Number and the orientation of orbitals. The final quantum number is a spin quantum number, and that's for the electron. The electron has two orientations. The electron can be spin up, which we call plus 1/2, or spin down, which we call negative 1/2. So this, I copied this, put it in a slide. I didn't copy these. You don't really need to know that. Yeah. We represent energies, allowed energies, as lines or boxes. We represent arrows as electrons, or we represent electrons as arrows, I should say. So this is an electron with its magnetic spin up, which we call plus 1/2. This is an electron with its magnetic spin down, which we call minus 1/2. And so these are called spin orientations. Spin orientation. There's only two spin orientations for an electron. It could either be spin up or spin down. This is the Pauli exclusion principle says max of 2. We can't put 3, and they have to be opposite spin. That's another thing Pauli exclusion principle says. They have to be opposite spin because they can't all have the same set of 4 quantum numbers. The first 3 quantum numbers define the orbital, and the last quantum number defines the spin. So here's filling electrons in. 2 max, opposite spin. 2 max, opposite spin. This is an orbital box diagram. This is not an energy level diagram. It's more compact. Your book's answers are going to be like this. It's not as descriptive as this. This is more descriptive, but it takes up too much space. So your book is only going to have these types of things in there. Here is the map of, of all the quantum numbers here. When n equals 1, then the only L value that's allowed is 0. When n equals 2, we have 2 allowed values, 0 and 1. When n equals 3, we have 3 allowed values, an S, a P, and a D. N equals 4, S, P, D, F. N equals 5, S, P, D, F, G, that kind of thing. How many orbitals? When L equals 1, that's an S orbital. There's only one S orbital. And that's why we only have one value. This is 2s orbital. There's only one. This is a 2p orbital. There are 3, the -1, the 0, and the +1. You can see that. And so s orbitals, there's only 1. P orbitals, there's 3, -1, 0, and +1. D orbitals, there's 5, -2, -1, 0, +1, +2. F orbitals, when L equals 3, we have 7. -3, -2, -1, 0, 1, 2, 3. So 6 of those plus 0, 7 orbitals. Now the Pauli exclusion principle says that we put an electron in there and its spin is either going to be plus 1/2 or minus 1/2. So this orbital can hold 2 electrons, one at plus 1/2, the other minus 1/2. Pauli exclusion principle says that no 2 electrons in the same atom can have the same set of 4 quantum numbers. The first 3 define the orbital, and the last one defines if it's spin up or spin down. The rest of this table, ignore. So we have the energy level diagram here, and then we're going to fill it with electrons. Okay. Different ways of visualizing the energy level diagrams. These are all p orbitals here at different energies, 2p, 3p, 4p, 5p, 6p, 7p. It gets higher in energy. These are all s orbitals here. So this is why it looks funny, because they try to group the orbitals together, the p orbitals together, the s orbitals together, the d orbitals together, the f orbitals together, etc. And then we practice filling these with, and so we're going to get some practice filling these here. Let's do some right now. So for example, hydrogen. Hydrogen has 1 electron. And so that 1 electron is going to be in a 1s orbital in the ground state. So we can do this. It's either spin up or spin down. This would be the hydrogen. Now, when I say 1s, that's a 100 orbital. And so this electron is going to be a 100 plus 1/2. This electron will be a 100 minus 1/2. 100 is a 1s orbital. And so Pauli exclusion says that no two electrons can have the same set of 4 quantum numbers. So if I try to put a third electron, or a third orientation, actually, no, this is hydrogen. I go to helium next, helium is going to have 2 electrons. And so one I could spin up, the other I could spin down. If I go to lithium, lithium is going to have 3 electrons. I can't put the third electron here because it either has to be spin up, and so I'd have 2 spin ups, or it has to be spin down. I'd have 2 spin downs. So it's got to go up here, either spin up or spin down. It doesn't matter. That's lithium. And then beryllium, like this. And then boron, like this. Now, Hund's rule says this. I'm just going up. Off-bow principle says fill these from lowest to highest, So the next highest would be 2p. Hund's rule says that we're going to fill these one at a time with parallel spins. So that's boron, this would be carbon, this would be nitrogen. Then when we get to oxygen, we have no choice, but we got to pair this. So this is oxygen, this is fluorine, this would be neon. Then we continue on. This would be sodium, magnesium, as we put electrons in the orbitals. So we're going to get some practice putting electrons in orbitals. And so here, if we look at magnesium, this is one way of representing it. The other way is we could write the quantum numbers for each individual orbital, 100 for the 1s, plus 1/2 for this electron here. If I look at this electron here, I can map it out. That electron there would be called a 210 minus 1/2. And so we could give a unique set of numbers to every single electron in here based on how we mapped it out. That's what we need to do. Okay, this is kind of, magnesium, there's a compact way of writing this, but we lose some information. The compact way of writing this is via electron configuration. So it'd be 1s2, 2s2, 2p. Now the 2p, the whole thing has 6 electrons. So we say 6 electrons, and then 3s2. This is called an electron configuration. Not as much information, but more compact. That's it. All right, it's break time, but this break is going to be an extended break. I'm going to stop talking about quantum now. We're going to switch gears and go to lab, but I'm going to leave here. I'm going to go to the lab, so it's going to take me a little longer. So let's take an extended break right now. So let's take a 30-minute break. So it's 1:45. Let's meet again at 2:15 because I need to set up over there a little bit. So maybe 2:15, maybe 30 minutes too long. Oh well, yeah, let's go with a 30-minute break. Okay, so we'll be back at 2:15. I'll see you then. Let me pause the recording, or I'm going to stop the recording. We'll restart the recording when I get to the lab. Okay, all right, thanks.